So we want to show that gamma density function is a valid density function. The gamma density function, I'm going to write it as f of x, is given by 1 over gamma n lambda to the n x to the n minus 1 e to negative lambda x. So that is what the gamma function looks like. Again, this is the probability density function, and of course here x has to be positive. Okay, now the density function is going to be 0 if x is negative. Okay, so in other words, we can write it as 0 for x less than 0. Okay, so to show that the density function is a valid function, remember the function must be positive, which you can, by inspection, see that the gamma function is positive function. Let me write the gamma function actually itself. The gamma function that I have in mind, gamma n, is given by the integral from 0 to infinity of x to the n minus 1 e to negative x dx. Okay, and of course we have the restriction n has to be positive. The gamma function generalizes the factorial function. Okay, so this function is indeed positive. Now the other thing we have to check in order to make this a valid density function is that the area under the curve has to be 1 over the domain of the function. Now that's what we want to show in this video. So if I write the integral for the density function as 0 to infinity of 1 over gamma n, and I have lambda to the n, x to the n minus 1 e to negative lambda x dx. Okay, so if this integrates to 1, then we have established that the density function is indeed a valid function. Now to integrate this integral, I'm going to do a couple of things. First, I'm going to let the new variable u represent lambda x. And with that, du ends up being lambda dx. Okay, so from the original substitution, we can see x is mu over lambda. Now, for our integral, I'm going to bring out 1 over gamma n. And also, the other thing is the limits of integration. When x is 0, u, which is lambda x, is going to be 0. And as x approaches infinity, u approaches infinity also. So what that means is that I don't need to change the limits of my integration in here. Okay? But just to show that I did remember to check those limits of integration, I'm going to use a different color. Now, what remains is lambda to the n, and then instead of x, I'm going to use u over lambda to the n minus 1. E to negative lambda x, that's going to be e to negative u, and dx is going to be du over lambda, right? Right in here. So that's going to be 1 over lambda du. Okay, and then we can tidy up this integral a bit. Here's 1 over gamma n, limits of integration from 0 to infinity. Now, if you work these variables, I have lambda to the n, right? And then this lambda, bring it down here. Now I have also the lambda that's inside parentheses in the denominator of a fraction. That's going to be lambda to the n minus 1. So all of those lambdas are grouped together. Then I'm going to separate the numerator of the fraction to u to the n minus 1, e to negative u du. Now if I work all of the lambdas here, all of these, okay, lambda to the n crosses with lambda to the n, and lambda to the first to lambda negative 1 adds to lambda to 0, which is 1. So all of the lambdas practically cancel out. And when they do, I'm going to get 1 over gamma n, and then the integral from 0 to infinity of u to the n minus 1 e to negative u du. Now, this expression itself, indeed, this is the gamma function that we defined. I mean, you look back here. That was our gamma function. Okay, so I'm just going to replace that with gamma n. Okay, so at this point, we pretty much have established the validity of the density function, and this would be gamma n. And then, of course, this is equal to 1, and that is what we wanted to show, which establishes again the proof that the gamma function is indeed a valid density function.